My name is Christian Newman, the head researcher of the Source Code Analysis and Natural Language Laboratory. Today, I'll be discussing our part-of-speech tagging tool and its importance to identifier naming research. Before we get to that, I want to introduce you to my lab, Scannel. Scannel is interested in studying the latent connection between source code behavior and the natural language elements used to describe that behavior. We have a number of talented individuals working as part of the lab and plenty of interesting research, data, and tools that can help you pursue topics in natural language for source code. Please visit our webpage found at the bottom of the slide if you'd like to find our other datasets, tools, and research. In addition, the paper I will be presenting involves several of our members and collaborators, including myself, Michael Decker, Reem Al-Suhabani, Anthony Paruma, Mohammed Makawar, Satyajit Mahapatra, Tehal Vishnoi, Marco Sampieri, Timothy Sheldon, and Emily Hill. So this paper is about part-of-speech tagging, specifically a part-of-speech tagger designed to tag source code identifiers, which are often mistagged by off-the-shelf part-of-speech taggers made for typical English sentences. For the next few slides, I will discuss the importance of identifier names and how much we still do not understand about the practice and influence of identifier naming on program comprehension. This will help contextualize the importance of our part-of-speech tagging approach, which we will talk about toward the middle to back end of this presentation. Okay, so on to the topic. Identifier naming is an incredibly important area of research that has been worked on for a long time, but remains largely unresolved. There are still many open questions. In particular, we have no general way of measuring identifier name quality. We also have no general understanding of how identifiers or their characteristics influence comprehension. There are studies on these aspects, but there are no unifying theories about how these studies fit together. Given that identifiers make up the majority of the characters found in any given software project, it is untenable for us to remain largely unaware of their effect on the comprehension of both humans and automated techniques like artificial intelligences. One of the big challenges with identifier names is that they follow a different phrasal structure than English and other human languages. This means that we cannot use off-the-shelf NLP techniques on identifiers without potentially introducing significant threats. Using and creating natural language techniques for this problem is important though. Identifiers are how developers come to understand the code that they are reading, and they must read and comprehend code before they can do anything else. Whether that's adding features, fixing bugs, anything. They have to read the code first. Identifiers are also how some automated techniques analyze and understand code. Can we trust these techniques when the underlying information that they are using can vary in quality and we cannot measure that quality easily? If a technique relies on identifier name information, can it be trusted if the identifiers it relies on may vary in quality between systems? Because of the difficulty in measuring identifier name quality and our incomplete understanding of how identifiers influence comprehension of humans and tools, including AI, identifiers represent a threat to validity for any tool or research that leverages them until we have a stronger understanding of how to measure and discuss identifier name quality. So there are an absolute ton of challenges to identifier naming research and practice. In particular, measuring and analyzing the meaning of words that constitute identifier names, measuring identifier name quality from varying developer perspectives and experiences, and bringing more human-oriented perspectives to identifier naming research are all significant research directions that need to be pursued. In particular, the part-of-speech tagger I present today can help us with all of these bullet points, but I will focus on how it helps us deal with the first bullet point specifically. So the part-of-speech tagger is an example of a tool built for the specific context of identifiers in software, and a lot of Scannel tools are built from this perspective of software-specific tools. The motivation for the part-of-speech tagger from the perspective of our lab was to support grammar pattern analysis of identifier names. Grammar patterns help us measure, express, and comprehend identifier meaning and characteristics using part-of-speech tag sequences. They can be leveraged by humans or automated techniques for identifier name comprehension and analysis. However, the tagger is broadly applicable to many other natural language-oriented problems. Any problems that requires understanding identifier name semantics in the context of source code. If you're unfamiliar, part-of-speech taggers annotate words with their role within a sentence. The role is typically in relation to words surrounding a given word, which we wish to annotate with part-of-speech. However, in the case of annotating identifiers, which we can look at as small sentences, we should also take into account the surrounding code context. Because part-of-speech annotates words with a role, we can relate words that have similar roles, that is, words or identifiers with similar part-of-speech tags or tag sequences. So part-of-speech tagging is very useful for understanding identifier name semantics. Sequences of part-of-speech tags, such as those you get from tagging an identifier name, are called grammar patterns. So this is what a grammar pattern looks like. To get these, you split identifier names into their constituent words, then run a part-of-speech tagger on the split sequence. One type of part-of-speech is a determiner, which is abbreviated DT. Determiners are words like all, any, and the. The use of the determiner all in the fourth identifier implies not only what type of data this identifier represents, but also the behavior of the code nearby. We might assume that this identifier appears near the code that feeds it some kind of list of open file strings, and that there is no filter on this list since the identifier represents all of the open file strings. In addition, the use of a preposition in the second identifier implies a conversion action. Both the words to and from are common prepositions, and the grammar pattern in this second identifier is telling us that there is some conversion from something to a string. What is being converted to a string isn't obvious from the identifier, but it may be the calling object if this is a method, or perhaps this takes a function argument that will be converted to a string. The thing to notice here is that each of these grammar patterns can be correlated with different types of behavior: conversion behavior, population filtering behavior, collection style behavior in the case of plural noun phrase grammar patterns such as the one found in the third identifier. There are many different types of these grammar patterns, and we can use them to reason about both the semantics of identifiers and how one identifier compares to another by looking at how similar their grammar patterns are. In prior work, titled On the Generation, Structure, and Semantics of Grammar Patterns and Source Code Identifiers, we analyzed a significant number of these grammar patterns to taxonomize the different types that exist in software systems. We also manually annotated a large collection of identifiers with part-of-speech tags. This is a large portion of the data that we used to train the Ensemble part-of-speech tagger. If you are interested in understanding more about grammar patterns, please take a read of this paper. We also have another resource called the Identifier Name Structure Catalog. This catalog was built from the data in the grammar patterns paper discussed in the last slide. It documents the naming structures we discovered using grammar patterns, provides definitions for each grammar pattern, and examples of identifiers following those grammar patterns. Let's take a look at a couple of these, since one of the reasons we created the part-of-speech tagger was to be able to determine when an identifier is following these patterns. The catalog is filled with numerous grammar patterns discovered empirically through our research. On the left, you can see the grammar pattern. We use rag-style syntax to represent the pattern, so star means 0 or more, and bar means or. On the right side is a definition for the grammar pattern and examples of identifiers that fit this pattern. As stated earlier, many of these patterns are directly related to different types of code behavior represented by identifiers that follow the given pattern. We won't go into detail in this presentation, but this is a public resource for researchers and educators who want to learn more about identifier naming and find material they can use in their courses. All definitions are at the top of the document, so if anything confuses you, please read the top half. Now we're finally ready to talk about part-of-speech tagging in specifics. Identifiers have a different phrasal structure than normal English text. Off-the-shelf taggers don't understand this structure, so they cannot be relied on by themselves to tag identifiers. In addition, the behavior of the surrounding code can influence the part-of-speech tag that should be assigned to a word within an identifier, so this all must be taken into account by any part-of-speech tagger for identifiers. Another question is, Do the part-of-speech tags used for human languages work for source code? While our grammar pattern paper talks about this issue, and in that paper we argue for the use of a modified tag set, this is still very much an open question. The tag set used by our Ensemble Tagger is the modified tag set that we introduce in our grammar patterns paper. The primary hard part to creating a part-of-speech tagger is the amount and type of data needed. The training set requires both words and their correlating part-of-speech tags. And since off-the-shelf taggers don't understand identifier phrasal structure, they cannot easily be used to partially automate the problem, meaning that data collection is primarily manual. And since part-of-speech tag training algorithms are very data hungry, this can become a daunting task. So our Ensemble Tagger was accepted for publication at TSE. We will go over some details now, but please read the paper for full details on the implementation, metrics, and other types of information. Our Ensemble Tagger uses the output of 3 external taggers to help us determine the correct part-of-speech tag. These are SWUM, Posse, and Stanford Tagger. SWUM is a tagger designed by Emily Hill, Giri Prasad Sridhara, Patrick Francis, Lori Pollock, K.V.J. Schenker, and David Shepard. Posse was designed by Samir Gupta, Sana Malik, and Lori Pollock. Stanford Tagger was designed by Christina Tautanova and Christopher Manning. Posse and SWUM were designed to annotate source code identifiers specifically, while Stanford was designed for general natural language texts. We found that including Stanford helped to identify certain parts of speech that Posse and SWUM had trouble with, since it is very good at dealing with closed class tags such as prepositions and conjunctions. Alongside the 3 external taggers, the ensemble also considers certain word or code contexts, such as word position within the identifier, and whether the identifier represents a function, class, declaration, attribute, or parameter. These 5 features were all used because we empirically found them important for determining the correct part of speech for an identifier. These features are studied and discussed through both our work presented in the grammar patterns paper and their work presented in the Ensemble Tagger paper. So if you'd like more detail on how these features were chosen and why they were important for determining part of speech, please look at those papers. Using these 5 features, the ensemble generates a part-of-speech tag sequence for a given identifier. To train our ensemble, we augmented the dataset from our grammar patterns paper, which initially consisted of 1,335 identifiers made up of 3,449 words. The extension, which was 384 identifiers in size, was made so that we could have a completely unseen set of identifiers from systems that were entirely excluded from the training set, while maintaining the size of the dataset from the grammar patterns paper. This means that, in total, we had a dataset of 1,719 identifiers. The 1,335 identifiers were used in our train test datasets and were used for k-fold cross-validation. The 384 additional identifiers were not included in train or test, but were used after the k-fold cross-validation to see how accurately the tagger could annotate words in a second unseen context, aside from the k-fold validation. We tried around 9 machine learning techniques for combining the features that we discussed prior into an ensemble tagger. We determined that decision tree and random forest worked best for our task and dataset. The accuracy of our tagger when using the best model was 86% at the word level and 75% at the identifier level. One issue with tagging identifiers is that compounding errors can greatly lower the accuracy when it has to get the entire identifier correct. So even though it has high accuracy on individual words, if it gets even one word in an identifier incorrect, the entire identifier was considered incorrect. This is why the accuracy at the identifier level is about 11% lower than at the word level. The implementation of our tagger is publicly available. You can see the link at the bottom of the screen. There are instructions there for how to set it up and run it. If you have any trouble, please make an issue. The dataset that we use to construct the ensemble tagger is publicly available. to support future research in identifier naming and part-of-speech tagging. Let's click on this link and see what this dataset looks like. Visiting this link will bring you to the repo we have for our dataset. The README has information about the features that we use, including specific definitions about how we calculate different types of word positions in a given identifier, which you can find here. All of the other features are also listed in this and defined so that you can understand what they mean. We also have the tag set toward the bottom to help you figure out what the abbreviations mean, and you can find that here. One more thing worth mentioning is the context that you can see up here. We use context as one of our features, and the numbers to the left are what we use as the feature that gets fed into the Ensemble Tagger model. This right here is meant to help you figure out what those numbers mean when you see them in the training set. The training data corresponds to our 1,335 identifiers, whereas the unseen testing set is the 384 additional identifiers referred to earlier in the presentation. Let's click on the training data to see what's there. There's a lot of information in the file. Of particular importance is the identifiers and their types on the left, followed by a grammar pattern here. This grammar pattern is the correct grammar pattern. These were manually annotated by the authors of the original grammar patterns paper. After that, we have individual words that make up each identifier here. And this is why you see the same identifier repeated several times to the left here. It's because we feed individual words to the Ensemble Tagger, and it uses the normalized position feature, which you can find on the right here, to determine where in the identifier a given word appeared. Next to normalized position is a number corresponding to the context. As I said earlier, the README tells you what these numbers mean. To the right of that is the correct tag for the current word. The machine learning technique uses this to fit the output of the three taggers, Swum, Posse, and Stanford, and the two features, normalized position and context, so that we can use that information to obtain the most likely part-of-speech tag. The file actually has a bit more data than we use in this paper. Flare is another part-of-speech tagger, but we didn't include this in the original tool. We also record what system the identifiers come from, and a code for each identifier, which is way over here, to help reconstruct the predicted tags into grammar patterns. Feel free to make an issue or email us if you have any questions about this data set. And again, we hope this can help you with your future natural language tasks or in designing your own part-of-speech tagger. There are a few weaknesses in our approach for tagging. The first is that it relies on other taggers to understand word context. The Ensemble Tagger does not directly use features associated with probability, word frequency, or word embeddings. It's possible that adding this information as a direct feature could improve it. In addition, it is not possible to easily retrain Swum or Posse with more data because they were not designed that way. Stanford can be retrained. However, retraining Stanford could backfire if not done carefully. Finally, the Ensemble Tagger tags about one word per half second. We're currently exploring ways to make the tagger faster and have, in fact, come up with a few faster implementations that we may publicize in time. So today we discussed the Ensemble part-of-speech tagger designed by our lab, Scannel. The tagger is a step forward for identifier-specific part-of-speech tagging, achieving state-of-the-art accuracy at both the identifier and word levels. The tagger is pivotal in using grammar pattern style analysis, but is also extremely useful for almost any other natural language-oriented task. We hope the tools and techniques we create in this lab can help increase research in the area of identifier naming. There are so many problems to solve, and more researchers are sorely needed to solve those problems. If you have any questions, please feel free to contact us. In addition, we're always looking for feedback on our tools, the data sets, or the educational materials that we create. So please do feel free to leave an issue or to email us with advice or things that you think should appear in these materials. Thank you very much for your time.